Well, greetings everyone, and welcome to another edition of Takeo Tuesday. John Barba here, along with Rick Mayo, and we thank you for joining us on this Tuesday afternoon. I hope it's nice weather where you are. Here in the Northeast, it's unseasonably warm. We're coming to you today with very heavy hearts. This is going to be very difficult for us, but we have some very sad news to share with our friends out there. So I'm going to read a statement from Takeo. It is with profound shock and sadness that we inform you of the sudden passing of John Hazen White III on Thursday, November 3rd, 2022. The passing of John III, who we lovingly referred to as J3, is the son of Takeo Comfort Solutions owner John Hazen White Jr. and Liz White. Is a great loss to the Takeo family and all of our Takeo employees, friends, colleagues, and customers who had the pleasure of knowing him and his caring, big-hearted personality. We will miss him more than words can express. John worked in many positions at Takeo Comfort Solutions and was most recently Senior Vice President of North American OEM Sales, and he was loved by Takeo employees as much as he loved them. We extend our deepest condolences to his wife, Caitlin, and daughter, Madison Marie, his parents, John and Liz White, his brother, Ben, and his wife, Kirsten, their daughter, Winona Rose, Caitlin's parents, our colleague, Brett Zerba and Diane Zerba, and all of John's family members and friends. Further information on funeral and memorial services will be shared as we receive more details from the family. And if you wish to send a message of condolences to the family, please send to j3@takeocomfort.com. That's all there is. He was a wonderful guy, and we're going to try and get through this, but we're going to miss him. And he was a good man, very good man, and a wonderful father to his daughter, and a loving husband, and just a joy to work with. And that's all we can say about that. But I wanted to share that information with you before we get into talking about ECM and Bluetooth technology. Knowing John, he would have wanted us to carry on as best we could. So, all righty, second, we can go. All right, very good. Anyway, today's program is on ECM circulators and Bluetooth technology. The 0018E ECM circulator in particular, it's a product we've had out for about a few years now. And the importance, we want to share with you the importance of the Bluetooth connectivity, what the app can do, and also, again, just discuss ECM technology in general. And kind of continuing our theme of discussions on ECM technology and variable speed technology, I guess the question I'd like to send to you is, with a variable speed circulator, do you still need to figure out flow and head? Is this something we have to do, or can we just put in an ECM circulator and it'll take care of it because it is in fact variable speed? In your chat section, please, if you could do this for me, the folks of you that are out there, please just share with me your thoughts. Do you think this is still something that needs to be done, or can this circulator size itself? Let's take a couple seconds and just throw in a yes or a no for me, if you would, please. Do you need to still figure out flow and head if we're using variable speed? Because it is variable speed, right? Shouldn't it figure it out for yourself? I've got a couple here that say yes. Carmine says yes. Ryan says yes. Keith says yes. Ken says yeah. I think I think it's universal. Yes, good. We do have to figure out flow and head. There we go. And to get the max energy benefit, says Richard Baker. Yes, absolutely. Yes, the answer is a resounding yes. It is a resounding yes. Of course, you have to figure out flow and head, because that's how circulators know what to do. All right, it's all based on flow and head. You have to do those calculations, and the reason is it's not magic, it's science. Okay. They're not magic. I've heard people say, well, these things, it's the magic pump and it does the thinking for you and it takes the thinking out of it and it takes the guesswork out of sizing a circulator. Well, that's more than a little bit of nonsense. These are wonderful little creations. They do incredible things, but magic isn't one of them, okay? There's no Harry Potter here. There's no magic wand. They need to know what to do, because while they are not magic, they are incredibly obedient. They will tell you, they will do what you tell them to do. All right, they will do what you tell them to do. And they give us a lot more control. They give us the ability to program them as close to the flow and head requirements as possible. Now, in the old days when we had just single fixed speed circulators or 3-speed circulators, the curve would could get only so close to your flow and head requirement, and then that's where it worked, and it always worked on that pump curve. And if it was oversized, it was oversized, and it still worked. It still delivered heat, but it was oversized, and it would probably more than likely lead to short cycling, depending on how badly we oversized the circulator. That dynamic still is in play with variable speed circulators. We're still going to be working on a control curve, as we'll see. The difference is we have the ability to adjust that control curve to a much greater degree than we did with even a 3-speed circulator, to try and get the flow and head characteristics of the circulator in line with the flow and head requirements of the system. And if we take a step further and go to delta T, we might be able to get even closer. But one of the things about Bluetooth technology in the app with the 0018E is we can actually see where we are in relation to the requirements and adjust accordingly to a much greater depth. So we're going to look at that as we move along. But understand, variable speed circulators are not magic, no matter what anyone tells you, but they are obedient. They will do what you tell them to do, and that's what makes it fun. A real quick just overview on figuring out flow and head. We've gone through this before in Takeo After Dark and during Takeo Tuesday, but I want to make sure that we're kind of on the same page here as to how we figure out flow and head. You cannot separate flow and head. They go together like cake and ice cream, okay? As one goes up, as flow goes up, the head goes up exponentially. It's a function of the square of the increase. So, a lot of folks will look at a pump curve and just say, well, it's 8 foot ahead. That means it's max 8 foot ahead and you can't get any more out of that. No, you can pump a lot of fluid through a piping system, but the more you pump through a piping system, which is a fixed size, the head loss or the friction loss is going to go up at an exponential rate. And there's a math formula for that. Now, the formula for figuring out flow is something we've gone over many times as well. It is the universal hydronics formula. And that states that GPM, gallons per minute, the flow rate you need to deliver the BTUs required, is equal to the BTU load required divided by the product of delta T times 500. Let's identify those terms. BTUH, of course, is the heat load. If you're sizing a circulator for a zone valve job residentially, well, you size that circulator for the total flow of the house, for the total heat load of the house, because at some point, all those zone valves are going to be open and you're going to have to deliver all the flow. If it's a zone pump, the BTUH is the load of that particular zone. That's the numerator. The denominator, the number on the bottom of the division, is delta T times 500. Now, delta T is our designed for temperature drop of the fluid as it goes through the piping system. Typically in residential hydronics, we design to a delta T of 20. Water goes out at 180, comes back at 160. Or if it's a low temperature boiler, the water might go out at 140 and come back at 120. Typically a 20-degree delta T. Residential radiant, we probably look at a 10-degree delta T in many cases, but most normal residential hydronics, we'd be looking at a 20. The 500 is a mathematical constant when using 100% water. That is, if you multiply the weight of 1 gallon of water, 8.33 pounds, times the number of minutes in an hour, that's 60, times the specific gravity of the fluid, 100% water has a specific gravity of 1, times the specific heat of the fluid. Water has a specific heat of 1 BTU to raise 1 pound of water, 1 degree Fahrenheit in 1 hour, etc. 8.33 times 60 times 1 times 1 is 499.8. Heck, we'll call it 500. Now, Rick, if we were to add glycol to that solution, what would that do to the 500 number? How would that change? And how would the temperature of the fluid change that number as well?
It actually makes that number go down. It's counterintuitive, but as the number, let's say we were at 50% glycol, that number would drop maybe as far as 450. And the result of the calculation at 450, it slightly gives you more flow to compensate for the fact that that fluid no longer has the same ability to carry energy like good old H2O does.
Very good, right. And so as you add more glycol, the flow rate's going to have to go up. As the water temperature increases, even if it is 100% water, as the water temperature increases, the density goes down too, and that'll lower that number somewhat, not a ton, but somewhat. So for basic, just getting started and getting numbers on the ground, GPM equals BTUH divided by delta T times 500 works for us. Delta T times 500 works very, very well because 20 times 500 is 10,000, and by golly, you can divide anything by 10,000. It does make the math a little bit easier. For example, let's say we have a zone of something, and it's 30,000 BTUs, and we're designing it to a 20-degree delta T. 30,000 divided by 20 times 500 or 10,000 is going to give us a required flow rate of 3 gallons per minute. And that's a pretty good size zone. I'd say 30,000 BTUs residentially is a pretty good size zone. So as you can see, 3 gallons a minute, not a lot of flow. When you look at a 007 standard efficiency circulator, a VT2218 delta T circulator, a 0015E3, or the 0018E, 3 gallons a minute is well within that circulator's operating capabilities. And in fact, it's on the low end of what it can do. So 3 gallons a minute for a big zone. We've got circulators that'll do that without even breaking a sweat. This is where understanding the required flow rate is where something like the 0018E is going to become a lot more beneficial to you as we go forward. So that's the flow part. The head loss part is really, we're talking friction loss. It's not, we express head loss in feet of head, but it's not feet of height. We often think, well, hey, I got to pump that water up to the 3rd floor. How many feet is that? That's the feet ahead I need. No. It's just friction loss. We've already filled the pipe up. It's filled and pressurized. We did that with our static fill. So I don't have to lift the water up to the 3rd floor. There's already water there. And I don't have to worry about the height of the building or lifting the weight of the water because it's a closed loop system. And in a closed loop system, what goes up must come down. And in that case, I don't have to lift the weight of the water up. I have the same amount coming back down the other side as a counterbalance. Think of it as a Ferris wheel. So I don't have to lift the water up. All I have to do is overcome the friction loss of the pipe and fittings that water is going to encounter. And it's again, simple math. We just have to overcome that friction loss. The best way to figure out head loss, the most accurate way, is to use this chart in the Copper Development Association's Copper Tube Handbook. And you can go to the Copper Development Association's website and actually download this. It's about 160 pages of mind-numbingly boring stuff on copper. The most useful thing is table 6 in the back of the book. It's pressure loss of water due to friction in types K, L, and M copper tubing. And it gives you that friction loss in PSI per linear foot. Now, we're going to show you in a sec how to convert PSI to feet of head. Now, 3 gallons a minute, if we look at 3 gallons a minute, we understand our pipe sizing guidelines. At a required flow rate of 3 gallons a minute, we're going to be using 3/4 inch M copper tubing for our piping for this zone of heat. If we look at 3 gallons a minute right here and 3/4 inch M copper tubing, and we follow the row and column to where they intersect, we're going to see that in terms of PSI, we are going to have a pressure loss of 0.009 PSI for 1 foot of pipe, Our job now at this point is to figure out how many feet of pipe we actually have, starting from the Gazauta side of the circulator all the way through the system back to the Gazinda side of the circulator. So we have to estimate that run as best we can. And then we have to factor in fittings and things. So for our example, let's say we have 200 and some odd feet of pipe. All right, that's the length of the run. To allow for fittings and things that are in the way, valves and fittings, We can't count them, we have to allow for them. We multiply that by 1.5. What we'd be doing is we'd be allowing 50%, we'd be adding 50% of that total length to allow for fittings and valves and things that are in the way. For example, a 3/4 inch copper elbow has the same pressure drop as 2.5 feet of straight copper pipe. 45 has the same pressure drop as 1 foot of pipe. A T has the same pressure drop as 5 foot of pipe, et cetera, et cetera. So if we do the math, we measure and we multiply by 1.5, we come up with an example. For an example here, we come up with a total developed length of that zone of 285 feet. To figure out the pressure loss in PSI for the total loop, we're going to multiply 0.009 PSI per foot of pipe times 285 feet of pipe. The feet will cancel each other out, and we come up with 2.57 PSI. Now, to convert PSI into feet of head, we're going to multiply by 2.31. Why 2.31? Well, a column of water, we learned this, I remember back in my apprentice days, we learned this day one of plumbing school. A column of water 28 inches high will have a gauge pressure at the bottom of 1 PSI. Another way of saying 28 inches is 2.31 feet. So a column of water 2.31 feet high will have a gauge pressure at the bottom of 1 PSI. So to convert PSI into feet of head or friction loss, we're simply going to multiply 2.57 times 2.31 feet of head per foot of pipe. And that's going to give us 5.9 feet of head, 5.9 feet of head. We're going to call it 6. So this 285-foot zone of 30,000 BTUs will require a circulator that can deliver 3 gallons a minute at 6 feet ahead. Pretty simple and straightforward. Any questions on that out there, folks? I know that we've gone over this probably a million times in our different classes. I just want to make sure that we're all on the same page and there aren't any questions on that because it's pretty straightforward stuff. So
Nothing yet.
Beg pardon?
Nothing yet.
Nothing yet. Excellent. So 3 gallons a minute at 6 feet ahead. Our next job is to plot out a system curve. And a system curve is just basically, it's a fingerprint. It's a hydraulic fingerprint of this piping circuit. And each piping circuit has its own individual unique system curves. And as we said earlier, as flow goes up, head goes up exponentially. It's a function of the square of the increase. So there is a math formula for this. And I don't want to bore you with the details, but there is a math formula because there's a mathematical relationship between flow and head. And if we were to plot out that math formula, use that math formula to plot this out, and you can use it. You can also use it figure it out using the B&G system sizer wheel, which is a wonderful tool. My red dot here represents 3 gallons a minute at 6 feet ahead. Using our math formula, I can figure out what the head loss would be if the flow rate was 1 gallon a minute through that piping circuit, at 2 gallons a minute through that piping circuit. I know what it is at 3. Let's go to 4. Let's go to 5. We put those points on the plot and then we connect the dots, and that gives us our system curve. The reason the system curve is important is because the system will work where the system curve intersects the pump performance curve that we're working. For example, if I'm using the 0015 standard efficiency 3-speed circulator, it gives me 3 fixed speeds. If I'm using that circulator, the system could work either here or here or even here, depending upon which speed I choose. So if I choose high speed, because it's contractor no callback mode, boy, that's a 30,000 BTU zone. That's a long zone. I better give it all she's got, Captain, because I haven't bothered to figure out the actual flow and head requirements. I'm just going to put it on high and get the heck out of there. If I put it on high speed, I would have a flow rate of almost 5 gallons per minute through that zone. The pop quiz for you folks is, am I going to get heat? Will I deliver adequate BTUs to that zone? Throw in your answer or throw in your thoughts in the chat section. I'd be interested in hearing what you have to say. If I put it to high speed, will I heat that zone? And will I get adequate heat? Is it going to quote unquote work? What do you guys think? I got some yeses. Very good. Yep. Absolutely, it's going to work. Sure. I can deliver 30,000 BTUs with 5 gallons a minute all day long with hardly breaking a sweat. The thing that's going to change, however, because GPM equals BTUH divided by delta T times 500, my 30,000 BTUs under design conditions doesn't change. That's what I need. I don't care if I get more out of it. That's what I need under design conditions. I've now fixed my flow rate at 5 gallons a minute, not 3. Something is going to have to give, and that something is the system-wide delta T. It's never going to see 20 degrees. I will never have a 20-degree delta T there. The best I'm going to have might be about 14, 15 degrees, and that's under design conditions. As it gets warmer out and the BTU load goes down, that delta T is going to get smaller, 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 smaller. And I might spend maybe at least half, if not more, of the heating season with a delta T of less than 5. That means the water might be going out at 180 and coming back at 175. Or in a mod con boiler, it might be going out at 115 and coming back at 110. It's going to condense, I'm going to deliver BTUs, but is that boiler going to be as efficient as it could be, as it should be? Is that boiler going to short cycle? And is a short cycling boiler an efficient boiler? The answer to that is no. All right, so I'm going to get heat. No one's ever going to call you up and say, I'm freezing to death, it's your fault. But you got a system that's not as efficient as it could be or should be. And your customer didn't really get what they paid for, but they're not going to freeze to death. If I go down in speed to medium, I'm better. If I go down to low, I'm about as good as I'm going to get with that circulator. That's not a bad choice at all. And a word to the wise, if you use 3-speed circulators, man, low speed, if you use 3-speed circulators as zone pumps, I guarantee about 85, maybe 90% of the time, Rick, if you think it's higher, let me know. Low speed's going to be more than enough, more than enough. If you start getting into radiant heating or using a lot of PEX tubing, well, we might have to talk about that. But copper fin tube systems or anything with copper piping, yeah, low speed's going to be plenty. Low speed's going to be plenty in those cases.
When they pencil it out, many times low speed is actually more than they need.
Yeah.
But if they're just guessing, and if you're just going to guess, start with low speed.
Yep, absolutely, absolutely. And guessing, well, yeah, the thing about guessing, I've learned this a long time ago. If you guess, one of 3 things can happen, and 2 of them aren't good, right? You could guess absolutely spot on right, and that would make you the chosen one, right? That you are the chosen one. Or you guess high, and high, as we've seen, can overpump. You're still going to get heat, but we've really intentionally limited the performance and limited the efficiency of the system. Or you could guess low, and if you guess low, you're going to get a phone call. So I guess 2 of the 3, if you don't care really about the efficiency and you just you're playing roulette and you don't want the phone call, if you guess right, you're okay. If you guess high, you're okay. If you guess low, you're not. You got to, 2 out of 3 ain't bad. That's what Meatloaf said. So I could see why the guessing would be attractive, but knowing is way better than guessing, especially if you're professional and you have a shirt with your company name on it, in my opinion. All righty. So with that as a background, let's get into variable speed. What does variable speed do for us in this situation? Well, again, let's take a look at the 0015E3, 3 gallons a minute at 6 feet ahead. Okay, we're right here. 3 gallons a minute at 6 feet ahead. The 0015E3 is a 3-setting variable speed circulator. I could set it to low speed here, and at low speed, it might be down right around here. Is that going to work? Let's see. I probably, if we were to carry out the system curve at medium speed, I'm at about 10 foot ahead and maybe a little bit more than 3 gallons a minute. And if I go to high speed, maybe I'm up here at about 4.5 gallons a minute at 16 feet ahead. Again, same thing. It's going to work on one of those performance curves. The thing that makes it variable speed is if I'm up at full speed, that's full speed, fixed speed, 44 watts. As a zone pump, a variable speed circulator is not going to vary its speed during operation. But what it will do is it'll find its happy point and work at a specific speed automatically where the system curve intersects the performance curve. So if I set it to full speed, I'm at 44 watts right here. That's 44 watts. If I chose medium speed, I'd be, let's say, 3.5 gallons a minute, but I'd be working on a pump curve right about here that might be, oh, I don't know, let's say it's 28 watts. So I'm saving some electricity there. I'm still over pumping, not by a lot, but I'm at 28 watts instead of 85 watts or 90 watts with a 3-speed circulator set to maximum speed. So I'm saving some wattage there. If I choose low, maybe I'm down to about 15 watts, but would you choose low for that example? Because I'm not going to get 3 gallons a minute. I might be looking at about 2.5 gallons a minute. What would that be a problem? Rick, what do you think would happen if I went with low speed for that actual application?
My opinion is it would work just fine. Just the nature of the fudge factor we have built into those
Yep.
initial calculations that we used. However, even if it was right out to the end there, your delta T is going to widen slightly, ever so slightly. That's not the end of the world. And we've got lots of classes on that as well.
Absolutely, yeah. I think you're absolutely right, Rick. If we set that to low speed, we'd be heating this house with 15 watts of pumping power, which is tremendous. Most of the heating season, we're going to need less than that 3 gallons a minute at 6 feet ahead. So most of that heating season, your circulator will in fact be oversized, right? As we get closer and closer to design conditions, your quote unquote coldest day of the year, which is really roughly 2 to 2.5% of the heating season, we won't be able to deliver 3 gallons a minute, but that GPM equals BTUH divided by delta T times 500 thing comes back to play. As Rick said, the worst thing that's going to happen is, in this example, your delta T might stretch out. If our calculations were spot on accurate, your delta T might stretch out to 22, 23 degrees. Not the worst thing in the world. Definitely not the end of the world. So in that example, sure, now the variable speed works in our favor. We could set it to low, maximize the electrical efficiency of the circulator, and still make sure the system operates adequately. Okay, so just a thing to consider. So just again, a way to look at this. Now, if we were to, and yeah, there's our system curve plot. If we were to, whoops, let's go here. There we go. If we were to look now at the 0018E and see what the Bluetooth can do for us in this example and in others, we can actually set this thing up to be as accurate as a circulator can get by using the app to further program the circulator rather than just settling for what's on the dial. We can really dial this thing in to be a perfectly sized circulator. So the 0018E it's very simple to use. We have a Bluetooth, we have an app that you download, the Takeo 0018E app. You download that for both Android and iPhone. And you connect via Bluetooth to that circulator. You need to be in proximity to the circulator, and you can connect via Bluetooth to that circulator. And you have two ways of using the app. You can use it as a read-only app, or you can use it as a read-write app, meaning you can read what the circulator is doing as well as program the circulator. So for one-way communication, we can connect via Bluetooth, but we will use the dial on the circulator to actually program. And there are 3 operating modes on that circulator. The first is what we call the blue mode, which makes it an infinitely adjustable fixed speed circulator. So if you look from min to max here, we have a volume dial. Basically, you turn that thing more up to the right, the circulator will go faster. You turn it back to the left towards min, it'll go slower. And you will be able to see on your app kind of where the circulator is operating, where that little there's a little bouncing ball here that you'll see in a minute, where it's operating. So you can fine tune you can fine tune your flow and as a result, your head in that piping circuit. But when you do read write, it gets a little bit simpler. If you were to go to the ZV mode, that's the zone valve mode, that's a constant pressure, flat curve, variable speed operating mode. We could go to either 10 foot of head or 15 foot of head for zone valve applications, medium or high settings. Additionally, there's the green mode here, which is the thermostatic radiator valve mode for circulator that size. We're looking at panel radiators, parallel piping, home run to radiators with thermostatic radiator valves and continuous pump circulation. And we have two proportional curves to choose from, both the medium and high. And that's just read only. If you don't want to use the app to program the pump, you can use the app to simply read what the pump is doing. All right. If you get into two-way communication, that means you turn the dial all the way to the left to that Bluetooth insignia. Now we engage the circulator and we can use the app to program the circulator. And it opens up a world of possibilities. We have both the blue setting, which is infinitely adjustable variable speed, and we have the orange setting, which is constant pressure for zone valves. But whereas on the dial for the zone valve application, we had two different performance curves, using the app, we now have 9. So if I know my flow rate, and say I have a zone valve job and I know my flow rate, I can simply set and know my head loss. I can simply select using my finger on my phone. So just be real simple, just kind of like that. I can select the pump performance curve that's going to best fit the job. In the blue mode, for zone pumping, if I know the flow rate, I don't even have to figure out the head loss. All I need to know is the required flow rate. Using this blue dial right up, this blue dot on this little slider, I can adjust the speed of the circulator until I get the flow rate I want. It will determine the head for me. I don't have to even bother. Okay, so that allows us to get right down to that 3 gallons per minute on the button application, or that setting for that circulator for that zone that we just discussed. Additionally, there are 2 other operating modes for proportional pressure applications. The green mode is a user selectable proportional operating curve, where again you use your finger, pick the line, touch the line you want, and that's where it'll operate. And then there's what we call ActiveAdapt, which again, using continuous circulation, it's something we'll explain in detail in just a few moments. Using continuous circulation with modulating thermostatic radiator valves, the circulator will adjust as needed to the proportional pressure curve that's going to best reflect the needs of the system at a given point in time. It's not the same thing as throwing it in a zone valve job, pressing the button, it'll size itself, because that is a myth. That does not happen in anybody's circulator. We're going to show you how that ActiveAdapt, that automatic mode, works in just a few moments. But then you have your 4 different operating modes within the app. If you have here's your operating curves for both zone pumping and zone valve applications. So in a zone pumping application, that circulator can work anywhere within that blue mode. I simply adjust the speed using the slider, and I can get it to work anywhere I want within that blue mode. In the orange mode on the left-hand side, again, I can simply select which one of those flat constant pressure curves that's going to best fit my zone valve application. And again, I just use my finger to select the right one. If I'm going to set constant speed mode, here's some basic steps on how to set the constant speed mode. Again, you see the slider right here that'll allow me to set the speed. And if you take a look down at the bottom, you'll see that the app will tell you flow, head, wattage, and RPM. It'll all be shown down at the bottom. So the way to use this app, get an idea of the load. So say you're using it as a zone pump, get an idea of the load, whether you do a heat load calculation or you interpolate as best you can, get an idea of the BTU load of that zone, and then convert that load to a flow rate using the universal hydronics formula, GPM equals BTUH divided by delta T times 500. Once you know the flow rate, life is easy. You simply move the slider until you get the flow you want down at the bottom, until you get the flow that's required down at the bottom. So you simply adjust the slider, that blue dot will move pretty much on the performance curve, or on the system curve rather, of the piping system itself, and you simply adjust the speed until you get to as close to 3 gallons a minute as you can get. You don't have to figure out the head, because the head will be a result of flow through that piping circuit, and the app will tell you what the head is. So it makes it really, really simple. You basically have to do half the work. Just figure out the flow rate, move the dial, and the app will take it from there, which works out very, very well. If you are, and that's for you for zone pumping, setting up in constant speed mode. Now, if you have a zone valve application, and you want to set a constant pressure mode, select the constant pressure line that you need. Well, again, same thing. Step one, get an idea of the load. That would be of the entire house, because again, all zones calling, that circulator under design conditions is going to have to give you the flow for the entire house. So you want to figure out the flow for the entire house that circulator is going to have to provide. And then you convert that load to flow rate using the universal hydronics formula. So let's say you had a house that was 70,000 BTUs. Well, 70,000 divided by 10,000, I'm going to need 7 gallons a minute for that entire house for my zone valve job. Call it 7 gallons a minute. Now here's what you do for zone valve applications. The first thing you do is you switch from your zone valve orange mode back to the constant speed mode. Go back to the blue mode. And here's what you're going to do. You're going to adjust that slider until you get the flow rate you want down at the bottom. So adjust that until you get your 7 gallons per minute. When you get your 7 gallons per minute, take a look down at the bottom, and it's going to tell you the head loss at 7 gallons a minute. So again, you don't have to figure it out. It's going to tell you the head loss. So in this case, let's call it 10 feet ahead. We're going to call it 10 feet ahead. So if we have 7 gallons a minute at 10 feet ahead, now I'm going to switch back to, just by pressing this icon right here, I'm going to switch back to my constant pressure orange mode, and then using my finger, I'm going to press the line that I want. In this case, it's the 10 foot ahead constant pressure line, and now that's where it's going to work. So again, using the app, you don't have to figure out the head loss. The app will interpret that head loss for you. If you know the flow, it will figure out the head for you, and then you can work from there. In zone pumping applications, you just have to program in the flow. In zone valve applications, once you know the flow, you program that in, it'll tell you the head, you go back to the orange mode and press the button. Any questions on this, folks? This is it's kind of interesting, and it really changes, and when you're out in the field, it changes the way you set up circulators. In my mind, it makes it, there's no reason to guess. Now you can know, and you can know very easily. All
Don?
you need to know is the load, and you can take it from there. Yes, Rick?
No questions yet, but on that fixed speed, let me throw out another question if we got a second. What
Sure.
other applications might we want to use fixed speed for other than just zone pumping? And see if they'll give us an answer.
Very good question. And under what other circumstances might we want to use the fixed speed mode here to set up the fixed speed that we're looking for? What do you guys think out there? I can think of 2 right off the top of my head. One of them is real important. How accurate is the GPM? The GPM is about as accurate as you can get. Is it off a point or two? It's not off a gallon or two. It might be off a decimal point or two.
Engineering told us it's as accurate as a typical circuit setter, and most people put their trust in those all day long.
Sure. There you go. There you go. And that might be a decimal point or two. Yeah. Very good. Very good. Question: under what other circumstance might you want to use that fixed speed, adjustable fixed speed mode. Let's see what you got. Come on, people.
Nothing's coming in, John.
Oh my gosh. Oh my gosh. We might have to flip all the cards here, Rick. Where were you going with this? I think I know, but where were you going with this?
I'm just saying, I'm thinking of a couple of as well, but the one that we've done some classes on is when you have a primary boiler circulator in a primary secondary condensing boiler application, and you don't have 0 to 10 for whatever reason, either the boiler doesn't have it or the pump doesn't have the ability to receive it, you want to size that circulator way out as far as you can on the temperature differential. So we use that universal hydronic formula. We figure out how many GPM we need, let's say at a 35 or a 40 degree delta, and then we set that pump way out there. We set it down, so to speak, to where it really should be, so that the delta T under a design load condition is going to be right where it needs to be. Adding more to that is that the boiler circulator tends to be way oversized too often, and that leads to the overall system efficiency dropping.
Right. As Rick said, if you have a ModCon boiler and you want to size the boiler pump to get the maximum efficiency out of that boiler, size it to as wide of a delta T as the manufacturer would allow, they'll tell you what that flow rate should be. So maybe it's only 4 gallons a minute or 3 gallons a minute through the boiler's heat exchanger. When you have the app, you just simply move the dial to 3 gallons a minute or 4 gallons a minute or whatever it is. It'll deal with the head loss. And now you have that circulator sized about as well as a circulator can be sized for a ModCon boiler. And as Rick said, it's impossible to understate, or it's impossible to overstate rather, how important that is to the boiler's performance and the system's performance. Because let's say you have a variable speed circulator on the system, and you have the circulator sized perfectly for the boiler. All right, now both are going to be in balance really nicely, and we're going to minimize the amount of the occasions where you might get flow backwards through the closely spaced T's. It's going to happen no matter what you do. But but the biggest element to that isn't the variable speed circulator on the delivery, it's the speed of the circulator on the boiler. And you size, if you know what you're doing and you size that, you're going to minimize that and make sure the system is as efficient as possible. Brett came up with a question. What about when the pump only sees the cooling house load and a geothermal fed cold storage tank? Well, whereas I'm not a geothermal guy, so I'm going to guess, Brett, that might actually work well for you there too. Rick, did you have a comment on that?
No, at this point in time, that little 0018 is not potted, so it's not approved for cold water applications, but it will be soon. And then the answer would, of course, be yes. You just need to tell us what your GPM is based on the cooling load, typically tighter delta T's, at 10 or 8 or something along those lines. And then you dial it into the GPM number, and then it would work. Yes.
Very good. Very good. Excellent. Great question. So what's the last portion of the program? Just want to say, what is the deal with ActiveAdapt? How does ActiveAdapt work, and what does it do? The legend that we've talked about many times in our classes is people think, oh yeah, you press the button and it sizes itself automatically because it's European, man. Well, not even close. That's not what any of them do. We got to understand what it was designed for in the first place, ActiveAdapt. It's designed for a typical European style heating system where you have a ModCon boiler with panel radiators, okay? You have panel radiators out there. And it's a 2-pipe system, meaning you basically have a manifold and maybe a PEX supply and return line to each radiator from that central manifold. And we have thermostatic radiator valves, as we show here, on each radiator. What you have is one circulator that runs 24/7, okay? It's continuous circulation. It never shuts off. It runs continuously. The thing that determines the comfort level in each room is the TRV. Those TRVs will modulate. They'll be opening and closing based on the comfort level in the room and how cold it is outside, obviously. That's your typical European style heating system going back to the 60s. Okay, that's how they've done it because that's how they've always done it. There's nothing inherently better about it. It was just the easiest way they had to retrofit systems into existing structures. So that's your typical European style heating system. Now, if let's play a little Goldilocks here, and you could have a pump that's too big, you could have a pump that's too small, or a pump that's just right. If the pump is too small, okay, if the pump is too small, you're going to have situations where the valves will be mostly open, okay? We'll spend a lot of time way out here. If this black line is your comfort center line, the valves are going to spend an awful lot of time open out here, and then they'll close for a little bit, and then they're going to be open for a lot of the time. The net result is going to be inconsistent temperature control and inconsistent comfort. If your circulator's too big, if we overpowered it, then we've got to have the exact opposite. We're going to spend a lot of time with the valves mostly closed, and then they're going to open, and then we're going to spend a lot of time mostly closed. And the net result is going to be about the same. We're going to have inconsistent heat delivery, inconsistent comfort in the rooms. So with ActiveAdapt and all of the other variations that other manufacturers have, what's going to happen is this. As long as that pump runs continuously, all right, it's going to assess changing pressure differentials as those TRVs modulate, and it's going to select the best proportional delta P curve. Again, that descending curve. It's going to determine the best delta P curve to work from. And as things change, it might bump one up or bump one down, depending. It's not going to be, running all over the place, constantly changing. It's going to be a very gentle jump, maybe one up, maybe one down once it's kind of figured out where it needs to be. The goal here is to, if we go back to that football field, the goal here is to stay within the hash marks. So we're much closer to that comfort line. So we stay here and stay away from the extreme. So we straddle the comfort line a little bit better. The TRVs don't fluctuate wildly, and we have consistent comfort delivery. That's the goal of ActiveAdapt. So we try to do something along those lines. That's the goal. That's what it's designed for. Now, how does it get to where we need it to be? Okay, how does ActiveAdapt get to where we need it to be? Well, as you can see, we have 1, 2, 3, 4, 5, 6, 7 different curves that we can work from in our ActiveAdapt mode. There's 7 different proportional curves. At power up, we're going to default to curve 5 of 7. Now, when that circulator turns on, it has to do a few things. The first thing it has to do is it has to run for at least 90 minutes while operating on curve 5 to kind of analyze the system and see what's going on. After that 90 minutes, we need another 30 minutes to wait for the system to stabilize, okay? Because we're heating up and doing all that. Now we got to stabilize and the TRVs have to figure out where they're going to be. Once that happens, then the algorithms kick in, all the pre-programmed algorithms to help figure out where we might need to be operating. And if it needs to stay at 5, it'll stay at 5. If it's got to go down to 4, it might go down to 4. All right, that's where it's going to work. It's not going to jump down to 1 and then jump up to 6 and then down to 2 and then up to 7 as needed. It's going to find one that works, and it's not going to vary much from that. Here's basically what's going to happen. Let's say we're on 5 of 7, and as TRVs open and close, as TRVs close, we're going to slide down the proportional curve. As TRVs open, we're going to slide up the proportional curve. All right. In order for the circulator to change from one curve to another, either to go up 1 or down 1, the circulator is going to need to see a 1.3 gallons per minute flow change for at least 20 and even up to 60 minutes. So for example, let's say I'm working way up here, okay, at its highest point with my TRVs open. And now they open up a little bit more and I need more flow. All right, I need more flow and I'm getting, 1.3 gallon per minute change for 20 to 60 minutes. Once it does that, once it senses that, then it'll jump up to curve 6 of 7 and will work up and down that curve as the TRVs open and close. And this will happen, like I said, when it starts to get colder out per se. If it starts to get warmer out and my TRVs are mostly closed, I'm down here bottomed out, and now I get a 1.3 gallon per minute decrease in flow for 20 to 60 minutes, then it'll jump right back down to curve 5 of 7, and it'll operate on that curve. That's how AutoAdapt, ActiveAdapt, all the different adapts work. That's what they're designed to do. So they'll jump up and down depending upon those flow changes. Okay, it's not sizing itself, so to speak, it's adapting automatically. And what we want in steady state operation, ideally, because that pump's running continuously, is to just bop up and down two curves kind of like that. That's really the ideal steady state operation. All right, just bopping up and down one curve as needed to stay within those hash marks, and the TRVs modulate to make sure we keep relatively steady comfort in those rooms. That's how it works. Okay, that's how it works. If the circulator should shut off, you go back to the beginning. Okay, you either start where you left off, okay, and then it's got to go through that whole hour and a half, 2 hour thing again before it figures out what to do, or it's going to go back, just go back to default curve 5 and start the whole process all over again. It's kind of how it works. Okay, that's kind of how it works. And again, what we want to do is get the circulator working, get the system working within those hash marks instead of outside of the numbers on the football field to maintain a nice comfort level. All right. If we were to use ActiveAdapt in a zone valve system, so let's say I have a system that's 7 gallons a minute at 7 feet ahead. This is where I want to operate. That's my requirement. Well, again, we're operating on curve 5 of 7. That's the default. So when that system starts up, we're working right there. And that's going to be at about what looks to be about 9 gallons a minute at about 10, 11 feet ahead. That's where it's going to work. It has to. It has to. As zones open and close, let's say I have my highest head zone, okay, is 3 gallons a minute at 7 feet ahead. That's where it wants to operate. All right. But as my zones close, what's going to happen is my operating point's going to go up and then down on that proportional curve, and I'm actually going to be working right here. Okay, that's where the system curve intersects the pump curve for that one zone. Let's say my smallest zone is itty bitty. It's 2 gallons a minute at 2 feet ahead. It's an itty bitty zone. This is where I would want the circulator to work, but because system curves sometimes get a little weird, all right, it's going to actually operate up there. This is one of those weird instances, and it happens with variable speed circulators. It happens with fixed speed circulators, that the circulator might be running faster or delivering more flow for a small zone than it would for a larger zone. It's weird, but it's just how the math works and the pump curve works. So in this example, my lowest head zone, my smallest zone, 2 gallons a minute at 2 feet ahead, actually going to be working way the heck up there at about what looks to be about 4, maybe even 5 gallons a minute at that point. And because the circulator turns off, I'm never going to adapt. It's never going to work on anything other than that number 5 performance curve. And that's going to be true of anybody's circulator. If it doesn't, because the pump turns on and off, which is what we do with zone valve jobs, it's never going to work any differently. It's going to look like it's working. Okay, it's going to work. You're going to deliver the BTUs. No one's going to call you and say, I'm freezing to death and it's your fault, pal. You're never going to get that phone call. And if you look at the circulator, if you look at the readout on the pump, or you look at the app, you're going to see as zones close, it goes slower. As zones open, it gets faster. That little 2 gallon a minute versus 3 gallon, that's just weird. All right, but hey, it's doing what it's doing. It must work, right? System's going to work just fine. We're not automatically adapting to anything. Okay, it's just working on that curve, and that's all it's ever going to do. In a zone pump system, say I need 3 gallons a minute at 7 feet ahead, well, that's where I'm working right there. And it's never going to change. It's not going to adapt. It's not going to figure anything out. It's going to work where, excuse me, where the system curve intersects proportional curve number 5. And because There's nothing that's going to make the flow change, right? There's nothing modulating. There's nothing opening and closing. It even in the ActiveAdapt mode, nothing. And if I ran it continuously, nothing will ever change. It's going to stay right there because it has to. Because it has to. All right. I hope that that was helpful to you folks. That's kind of where we're at with our 0018E, and I hope that was a good explanation for you on the operation of ActiveAdapt. I'd love to hear some feedback from you. And again, time for you to ask as many questions as you want here, folks, on ActiveAdapt and on how it works and the value of the Bluetooth app for the 0018E. It is a tremendous little circulator. We've seen people say, I want to use it as a diagnostic pump so I can see what's going on out there, which I think is a cool idea. But then you're taking the pump out after you diagnose and putting something else in, which, okay, I get it, but now you've got a wet, now you got a wet pump. Say again?
I said, what's a man hour worth? You know,
Yeah,
how much money are you wasting to do that? So, I don't know.
Here's a question from Harvey on speeds low, medium, the impeller modulates. Does that still require the 90-minute runtime before it does that? If you're talking about the ActiveAdapt mode and proportional pressure, yeah, the impeller will let's say if we have zone valves or thermostatic radiator valves, as they modulate, we'll bop up and down the curve number 5, the default curve. We will go up and down. It needs 90 minutes to do something else. No, he says when the circulator is set to fixed speed. If it's a fixed speed, no, there's no 90 minutes. You control the speed with the slider. Once you set it with the slider, that's it. It stays there. It won't change. Let me know if that answers your question, Harvey. I want to make sure I understood it. Is that how you understood it, Rick?
Yep.
Okay. Let me know, Harvey, if we got it right. But that's a great question. Cool. All right. Keep them coming here, folks. That's what we're here for. I'm going to answer as many questions as we can for you on this Tuesday. Well, afternoon for me, morning for you, right?
Still morning for me.
Out there in beautiful Mesquite, Nevada.
Mesquite.
Is it nice and warm out there?
Well, it's going to get rainy and the wind's going to start blowing, but yesterday was 70. So
yeah, we were hit about 70 here as well.
Yeah.
Not going to be quite that warm today though.
Harvey's got another one about the standard efficiency 0015. So Harvey, no, that's a fixed speed pump. You got 3 choices for the fixed speeds, but it doesn't do anything automatically.
And if you're talking about the 0015E3, again, if you set low or medium, it's simply going to work on that curve. There's no changes in anything. It's going to work on that performance curve. The speed will change as zones open and close because you got different points where the different system curves are going to intersect that control curve. And as they intersect in different spots, the pump will slow down, the pump will speed up. But there's no 90-minute runtime needed. It's just as you set it to low or medium, it's there. And it's going to work on that performance curve or on that control curve, come hell or high water. It's not going to do anything differently. When do you anticipate the chilled potted version of the 0018E to be available? That I could not tell you, Brett. I know we have it for potable water. We have the potable water version that's out now for domestic hot water recirculation, but I'm not sure that I couldn't tell you when we'll have a chilled water version up. We do have the VT2218, our Delta T circulator does work with chilled water in those modes, so you can use that circulator, which the circulator varies its speed to maintain a specific Delta T. For what you're after. So that exists now.
Keith's got one. I'll take a swing at this one. How does the pump measure GPM as you slide the dial? Well, it doesn't really, none of these pumps measure GPM. None of these circulators that are ECM that give you a GPM readout actually read gallons per minute. What they're doing is they're just looking at an uploaded like a data logging clip that's gone up into the pump when we load the information into it. We've put these circulators on test benches and we've run them through all kinds of different scenarios. So, and we record all those scenarios in amp draw and RPMs and wattage and all that stuff. It's all on a graph. So if the pump feels a certain way, it can look back at the lookup table and say, oh, last time I was on a bench, that equated to X amount of GPM at X amount of feet ahead. That's all it's doing, is doing lookup tables on a bench test that's been data logged into the pump. Hopefully that helps. None of these things read GPM.
So it's a comparison of watts and speed, more or less. Yeah, I mean, it's resistance against the impeller, all right, will
Amp draw
equate to an amp draw. Based on that amp draw, it's going to say, okay, this is the flow and this is the resistance or the head loss I'm pumping against.
Yep.
So again, you say, I want 3 gallons a minute, it's going to speed up until it feels that kind of resistance, and the amp draw says, yeah, this is where we are. This is where we're at. So it's kind of cool. It's very neat. It's very neat programming, and it allows you to, again, get that system as dialed in as you can get a system. And when we're talking about efficiency, good enough really isn't, right? As they said, as Roy Kent said in Ted Lasso, don't you dare settle for fine. Whereas professionals, we have the tools to do it right and to maximize the efficiency. And if you're not doing this, if you're not, making sure the circulators are right, circulators have more to say about system efficiency than we've ever given them credit for. If you're not doing that part of it right, we're not maximizing efficiency. We can put in a wicked efficient boiler, but if we don't pump it right, that boiler is we're intentionally limiting the efficiency and performance of that boiler. And once you know, you can't not know. So it's all part of the process, all part of the package. All righty, folks. Hey, thank you so much for the gift of your time today. Rick, always a pleasure to see you. And keep J3 in your thoughts, please, people. A lot of folks never met him, but he was a wonderful guy, really special person. And make sure you hug the people that matter to you. And because you just don't know. You just don't know. So thank you all. Have a wonderful rest of your week. Rick, we'll see you tomorrow night, Takeo After Dark, right?
Yep.
All righty. And Takeo After Dark, 7 p.m. tomorrow. If you want to, we're going to be doing a little bit deeper dive into variable speed circulators. So if you want to join us for that, go to takeocomfortsolutions.com and you can register for tomorrow night's session, 7 p.m. Eastern time. We'd love to have you join us. All righty. Take care. Rick, we'll see you tomorrow night. All right. See you all next week as well. Take care, everybody.
Good day.
Bye.